Hello everyone, welcome to my third lecture on electrostatics. In today's class, we will learn what is electric dipole. We will also find expressions for electric field and electric potential due to electric dipole. And then we will find expression for torque acting on an electric dipole placed in an external uniform electric field. So let's start. These are the topics that we'll be covering today. What is electric dipole? Then electric field due to a dipole at axial point and at equatorial point. Next, electric potential due to a dipole at axial point and equatorial point. And lastly, torque acting on a dipole placed in uniform electric field. So in the beginning, let us have a look at the expressions for electric field and electric potential due to a point charge. These expressions we derived in our earlier class and are given by equations 1, 2 and 3. These expressions we are going to use in today's class. The electric field given by equation 1 shows that if the charge is negative, then the electric field will have a direction opposite to the unit vector r cap, because in that case electric field vector will be equal to minus 1 by 4 pi epsilon naught q by r square into r cap if the charge is minus q, means if it is negative. So similarly for potential also, if the charge is negative, then the expression 3 will have a minus sign. That means it will be given by V equals to minus Q by 4 pi epsilon naught R. So first let us know what is electric dipole. Electric dipole consists of two equal and opposite charges separated by a very small distance. If you look at the first diagram, you can see we have two charges, plus q and minus q. Both are having the same magnitude of charge q, but they are opposite in nature. One is positive, the other one is negative, and they are separated by a small distance. So they constitute one electric dipole. Now let us come to the definition of electric dipole moment. Electric dipole moment numerically is equal to the product of magnitude of either charge and the distance of separation between the two charges which constitute the electric dipole. And the direction of electric dipole moment vector is from the negative charge to the positive charge along the axis of the dipole. Now if you look at the second diagram, you can see the line joining the two charges, it contains the electric dipole moment vector, and it is denoted by P vector, and its direction is from minus q towards plus q. Now let us come to the derivation of electric field due to a dipole at an axial point. We consider a dipole which contains two equal and opposite charges plus q and minus q as shown in the diagram, which are separated by a small distance of twice a. Let P is a point which is on the axis of the dipole at a distance of small r from the center of the dipole O. Let the dipole moment vector of the dipole is denoted by small p vector. The direction of this dipole moment vector is shown in the diagram, and it is towards the right side, from the negative charge towards the positive charge. So to find the electric field due to the dipole, First we write electric field due to plus q charge, then electric field due to minus q charge, and then add them vectorially. The electric field at point P due to the plus q charge is given by 1 by 4 pi epsilon naught q by r minus a whole square into p cap, where p cap is a unit vector in the direction of dipole moment vector p vector. Here r minus a is the distance of the positive charge from the point P. Similarly, electric field at point P due to the minus q charge is given by 1 by 4 pi epsilon naught into minus q by r plus a whole square into p cap. Here r plus a is the distance of the minus q charge from the point P. So the electric field due to the dipole at the axial point P is the vector sum of the above two expressions, and it is then given by 1 by 4 pi epsilon naught into twice pr divided by r square minus a square whole square into p cap after the simplification. And one special case is there if small a is much smaller than the value of small r. That means if the separation between the two charges of the dipole is very small compared to the distance of the point P from the dipole, then under that condition the electric field due to the dipole at point P reduces to the expression 1 by 4 pi epsilon naught into twice P by r cube into P cap. So P cap, which is the unit vector in the direction of the dipole moment vector, denotes the direction of the final electric field. Now let us derive an expression for electric field due to a dipole at an equatorial point. Let one electric dipole consist of the two charges plus q and minus q separated by a distance twice a as shown in the diagram. O is the midpoint of the dipole and p vector is the electric dipole moment of the dipole. The electric dipole moment vector is directed from the negative charge towards the positive charge. The point P is situated at a distance of small r from the midpoint of the dipole O. To find the total electric field due to the dipole, first we write down the expressions for electric field at point P due to the two charges separately and then add them up vectorially. So first the expression for electric field at point P due to plus q charge is given by 1 by 4 pi epsilon naught q by r square plus a square, which is directed along BP, and it is because the charge at the point B is positive and therefore the electric field due to that charge is directed from the charge towards the point, so it is along BP. Similarly, electric field at point P due to minus q charge is given by 1 by 4 pi epsilon naught minus q by r square plus a square, which is directed along PA. This direction of the electric field due to minus q charge is along PA. It is because the charge is negative and therefore the direction of the field is from the point towards the charge. So it is along PA. The total electric field due to the dipole at the point P is therefore given by vector sum of the above two expressions, and both the expressions have two components each. The sign components are equal in magnitude and opposite in direction, and which is vertically upward and downward direction at point P, and they get cancelled. Only the cosine components remain, so that finally the electric field due to the dipole at an equatorial point is only due to the cosine components, and it is given by the expression EQ cos theta plus E minus Q cos theta multiplied by P cap with a minus sign, where P cap is one unit vector along the direction of electric dipole moment vector P vector. So the expression for electric field at equatorial point is given by minus twice Q cos theta by 4 pi epsilon naught 1 by r square plus a square into P cap. And putting the value of cos theta as shown in the diagram, cos theta is equals to a by under square root r square plus a square, and this gives our final expression for electric field due to the dipole at the equatorial point P as minus 1 by 4 pi epsilon naught P by r square plus a square to the power 3 by 2 into P cap. One special case is here that if the dimension of the dipole is very small, that means if small a is very less compared to the value of small r, then we can approximately write the expression for electric field as minus 1 by 4 pi epsilon naught P by r cube into P cap. This is because if a is very small compared to r, then a square may be neglected because it is coming as one additive term. So after neglecting, we get the final expression for E equatorial as minus 1 by 4 pi epsilon naught P by r cube into P cap. This is valid only if the dimension of the dipole is very small. Otherwise, the general expression for electric field due to the dipole at the equatorial point is given by minus 1 by 4 pi epsilon naught P by r square plus a square to the power 3 by 2 into P cap. Now we come to the derivation of electric potential due to a dipole at an axial point. Again, like the case of electric field, we consider the same dipole consisting of the two charges plus q and minus q with a separation between them as twice a and O as the center of the dipole, and let P is a point which is lying on the axis of the dipole at a distance of small r from the center of the dipole. And here also we follow the same procedure. We write down the electric potential at point P due to the two charges separately and then add them up. Here only the difference with electric field is that in case of electric field we added the two expressions vectorially, and here in case of potential we will add them just in terms of the magnitude, because potential is a scalar quantity. So first let us come to the expression for electric field at point P due to plus q charge, which is given by 1 by 4 pi epsilon naught q by r minus a. Here r minus a is the distance of the plus q charge from the point P. Similarly, electric potential at point P due to minus q charge is minus 1 by 4 pi epsilon naught q by r plus a, and r plus a is the distance of the minus q charge from the point P. So the total potential due to the dipole at the axial point P is given by the summation of the above two expressions, and it is equal to 1 by 4 pi epsilon naught q by r minus a minus 1 by 4 pi epsilon naught q by r plus a, and after simplification it comes out to be 1 by 4 pi epsilon naught twice qa by r square minus a square, so that we can write the final expression for electric potential due to the dipole at the axial point P as 1 by 4 pi epsilon naught P by r square minus a square. Here also we write the special case. If small a is very much small compared to small r, then the expression for electric potential due to the dipole at an axial point reduces to the expression 1 by 4 pi epsilon naught P by r square. Let us now come to the derivation of electric potential due to a dipole at an equatorial point. So again we consider the same dipole which contains the two charges plus q and minus q separated by a small distance twice a as shown in the diagram, and O is the center of the dipole, and let P is a point lying on the equatorial line at a distance of small r from the center of the dipole. Here also we first write down the expressions for electric potential at point P due to the two charges separately, and then add them up to get the final expression for electric potential due to the dipole at the point P. So first we come to the expression for electric potential at point P due to plus q charge, which is equal to 1 by 4 pi epsilon naught into q by under square root r square plus a square. Here under square root r square plus a square is the distance of both the charges from the point P. Similarly, electric potential at point P due to the minus q charge is given by minus 1 by 4 pi epsilon naught q by under square root r square plus a square. So that the total electric potential at the point P due to the dipole is given by V equatorial is equal to 1 by 4 pi epsilon naught q by under square root r square plus a square minus 1 by 4 pi epsilon naught q by under square root r square plus a square, which is equal to 0. That means electric potential due to the dipole at the equatorial point P is equal to 0. That means for every point lying on the equatorial line, the electric potential due to the dipole will be 0, whatever may be the value of the distance small r. That's all for today.